Hi everyone, so this is a tutorial video for the Matlab question in homework 3 of cell engineering, and it is based on the paper Construction of a Genetic Toggle Switch in E. coli. So before we start, I recommend going to the paper and just taking a good 20 minutes reading it. It's only 4 pages, so it's very short, but understanding what's going on in the paper will really help you do the homework. So just real quick on the background of what's happening here. Basically, if you look at figure 1, it tells you the toggle switch design. So the system is pretty simple. You have 2 promoters, promoters 1 and 2, and 2 repressors. And promoter 1 will express repressor 2, which will repress whatever promoter 2 is trying to express, and vice versa. So basically the idea is when one of them is going, the other one is not going to be on. So one of them is on and the other one is off. And that is a very stable thing. So they made it in a way that if, say, promoter 1 is going, then promoter 1 is going strong, and promoter 2 is going to be constitutively repressed, and vice versa, unless you introduce external stimuli, inducers 1 and 2, that will make it switch from the first steady state of promoter 1 being active to the second steady state of promoter 2 being active. So for more information, please look at the paper. So a main part of the code is asking you to recreate figure 2, which I have listed right here. So if you look at the captions real quick, actually tells you that it's the geometric structure of the toggle equations. So basically what it's trying to tell you here is that we're not actually putting in any data here yet. This is just to use their model, which they say will model the toggle switch system pretty well, and demonstrating what it can do. So let's break it down. So figure 2a is right here, and this is the bistable state. And you see that it's bistable because it intersects 3 times. The two curves intersect 3 times. Note that this is occurring at steady state, so there is no time dependence because we have du dt is 0, and same thing with dv dt, so this is at steady state and they are stable. And this system can be described by this system of equations right here, which is in box 1 of the paper. Please go look at that. But again, so basically if you set it at steady state, so the du dt and dv dt equals 0, so these two terms equal 0, you can rearrange the equations so that if you plug in the appropriate constants, alpha 1, alpha 2, beta, gamma, and then give it either v or u as the independent variable, then you can calculate the dependent variable. So let's look at the code and see how we do that. So I'm looking at the template here that's been given to you, and again you can see that we're setting, I think this is u, as the independent variable that we're going to vary. So we gave it 100 values between 0 and 25, and then we already have the two equations, 1a and 1b, inputted here. And then since the equations are related to each other, so basically right here you are calculating v, I believe. You're putting in u to calculate v, and then you're putting in v to calculate u, so that they're related. So the equation's already given to you, and we have a full figure here. So if I actually run this piece of code, run this real quick, we actually get this figure. And if we pop back to look at the homework, so if you look at the paper, this is actually the same graph as this, minus all the extra labels. But you know, because the two curves are intersecting 3 times, so 1, 2, 3, so this is the balanced bistable network. So figure 2a is basically done for you. What you're being asked to do is actually looking to create figure 2b. So again, figure 2b uses the same set of equations, but you're going to be changing the parameters slightly so that it becomes imbalanced and monostable. So how do we do that? If we look at the paper in box 1, we see that it defines the bistability in this way. So it says the bistability of the system depends on the cooperative repression of transcription, and it says the rates of synthesis of the two repressors must be balanced. If these rates are not balanced, the null clines will intersect only once, producing a single stable steady state. So that's exactly what we want. We want it to be not balanced so that we have one single steady state. So basically, when you're doing your code, you can copy and paste everything here. It's the same equations, but I want you to go read the paper and figure out how and what do you change in order for the rates of synthesis of the two repressors to not be balanced, and then go and mess with these equations a little bit. Hint, you'll be changing one of the four constants, or two of the, one set of the four constants, shall we say, and that will give you an imbalanced figure, an imbalanced system. So that's figure 2a and figure 2b done, and it's pretty simple. So let's look at figures 2c and 2d. So if I look at this, my first reaction is, what is exactly going on here? So to elaborate quickly, again, we are still kind of delving into the intricacies of this little model right here. And so what this is trying to say is, again, we're looking at steady state, so du dt dv dt equals 0. And basically, if you have them equal to 0, rearrange the equations and take the logarithm and substitute in everything, what you're going to get is you can technically plot log of alpha 1 versus log of alpha 2 and get two straight lines with beta or 1 over gamma as the slopes. So if you have some time and are really curious, go ahead and do that. So just do du dt equals 0, dv dt equals 0, and then substitute u or v, solve for u or v, and then substitute it into the other equation, and then do the logarithms, and you'll see that it works out. So basically what it's trying to say, if you look at the box, I believe, box 1, it actually tells you that the systems are bistable because beta and gamma are greater than 1. So this is trying to tell you that that is the case. So when beta equals gamma and they're both 3, you have a very large bistable region, and as you decrease what beta and gamma equals, you get less and less of a bistable region until, if you do beta and gamma equals 1, for example, not 1.1, then it's going to be one straight line here, and then there's going to be two monostable states and no more bistable states. So that's basically what it's trying to tell you. So when we actually do the graphing in MATLAB, we're going to use what's called a contour map, so it's not something that you guys have done before, but luckily most of the code has been given to you. But basically, instead of reproducing exactly what these look like, when you do it in MATLAB, you'll actually be doing 3 graphs. So you'll be doing one plot where beta equals gamma equals 3, plot 2, beta equals gamma equals 2, and then plot 3, beta equals gamma equals 1.1, okay? So let's step back into the code and see what's going on here. So looking right here, generating figures 2c and d. So still, we're not solving for anything, remember, because we're still just delving into the intricacies of the system. So this should be pretty familiar to you guys from last time, from the map kinase homework, where you had a number of points that you're running things through, and then setting up an array of zeros, for example. And right here, so this first plot, this first part of the code will generate a figure that replicates this curve right here when beta equals gamma equals 3. And I know that because if I look here, it gives me beta equals 3 and gamma equals 3. So that's what it's doing. And we are inputting alpha 1 and alpha 2 as the xy axes. So basically right here, we're actually inputting our alpha 1 and alpha 2, and also u as independent variables, and then solving for the outputs And so this part is pretty straightforward, just using equations 1a and 1b. So what could get a little confusing is everything from here down to here, this whole count situation. So it's a little complicated. If you really want to know, you can come to office hours and I can explain it to you. But basically, because we're doing a contour map, we're not actually plotting the actual values that we calculate. We're just going to say these if statements are basically being used to generate the contour. So with a contour, you have like different levels, and then it plots it in different colors or something, for example. So these if statements are basically what's determining whether or not we're inside the bistable contour or in one of the monostable contours, for example. So yeah, so it's like trying to determine if the toggle is going in one direction or the other, or if it's stable. You don't have to really worry about this in order to do the homework. But again, this little piece of code is complete. So if I do my nifty trick and I run it again, I'm just running this specific piece of code, then you see that I get this plot. So this is part of figure 2C. Let's go back. Or figure 2D, sorry. Actually, this is supposed to be exactly the same as figure 2C. So it should be this this outside curve right here. So again, you're just going to generate two more curves. You're going to generate this one and this one, following the same strategy here. So if I look back in my code, it's actually very, very simple because we're given most of the code already. So all we really need to change is what beta and gamma equal. So technically you can just copy and paste what's been done for this part into here and into here again, and you should get two more plots. That should give you the other two curves in figure 2D. Okay, so that is pretty straightforward as well. What's gonna probably trip people up is this third part, so generating figure 5a. So let's go back and look real quick at what figure 5a looks like. Okay. So figure 5a is the actual experimental part. So this is where they did the experiment and then they used it to fit into their equation, and then they're like, oh look, the model works and predicts what happens in real life. So in order to do this, I highly recommend reading the figure captions for figure 5a, so it's right underneath the actual figure in the paper, because that's going to give you a lot of information. But basically, let me run you through with what we're going to try to get out of this. So the blue curve is the monostable system. So it's the control plasmid is what they called it. And it does not have a switch-like response because you see as you increase the stimulus, it kind of goes up, the response goes up pretty gradually, so it's not too exciting. And then this red curve with the dots are the actual, they're the actual data, sorry. These are the actual experimental data points. So it's not continuous, but they took different points, and you see how when you get the input to be a certain point, it jumps very fast, and so that's the switch-like response. And then we have the red curve, which is actually also a single steady state, except it's in the high state versus starting from the high state versus starting from the low state. And so if you read the paper, you'll know what I'm talking about. But basically what we're trying to recreate here is this blue curve, this red curve that's described by the dots, and this red solid curve. And we're not going to worry about this orange stuff here. Okay, so let's look back into the actual code to see how we're going to recreate those curves in figure 5a. So obviously, because in the paper, equations 1a and 1b are differential equations, we are going to be using ODE solvers. Yay! So first, you need to actually define the parameters of the parameters, and these parameters are already given to you. These are the starting parameters, if you will, or the constants. And if you look at the paper, look at the figure captions for figure 5a, you'll be given the actual numbers they use to fit the curve. So just go in there and copy and paste those in. Okay, and then we list them in this little array. So basically it's these guys again, except now they're in array form in this array theta. So IPTG is the actual input. So let's look back at the figure again. So the concentration of IPTG is the independent variable that was varied in this experiment. So you're going to be doing that exact same thing here, where you are adding IPTG concentrations as your independent variable. And so we're going to use log space because in the actual graph they had it plotted versus a log x-axis, and you know what the boundaries should be just by looking at the actual axis limits. So you know how to do log space, put that in. And then t-span, remember from homework 3, is the time with which we're going to run the actual ODE solver. So here it's listed as linspace. You can use linspace to generate the number of values you want, or you could just give it an array, like I want it to go from 0 to 100, for example, and it'll still run, so it's not a big deal. Okay, this init, I-N-I-T, is the initial conditions. So if you remember from differential equations, in order to solve differential equations, you need like initial conditions or boundary values or something like that. So this is basically it. And this is pretty important. So you're going to want to define what U and V are at the initial conditions. And I recommend starting at 0, 0 to see what happens. So start at 0, 0. And then we have a for loop, because that's what we did last time as well for the map kinase homework, is we did a for loop. So for k equals 1 to something, hint, hint, you need to actually add whatever k equals over the higher limit for k, and it should be related to either your IPTG or t-span, so remember that, try to think through that. But here we have the theta given to you because we're running through each iteration of IPTG of k. And then this is your ODE solver, so we're using ODE23S again. So this should be very familiar. So the inputs for this function are equations, t-span, which you define up here, initial conditions, which you also define up here. This guy, don't be confused, it's just a placeholder for an extra option because we don't really want anything there, but we do want to give it theta values. So you don't have to change anything about this line. Don't get confused about the brackets. You don't have to put anything into the empty brackets. It's just a placeholder. Okay, so another thing that you need to do, so last homework, all the equations were given to you, but for this homework, if you scroll down to where it calls the equations that you're going to solve, it's actually, oops, that was my timer. But anyway, so the actual equations that you are being asked to solve are not actually given to you. It's not complete, so all of this stuff is fine. But down here, you're going to need to put into your equations. So dy dt1 is just equation 1a from the paper. So let me pull that up. So it's going to be equation 1a from the paper, so that's pretty straightforward. Now dy dt2, I will give you a hint. You need to look at the actual figure captions for figure 5a to figure out what you're going to be putting in. It's not going to be, so you can't just put in equation 1b like straight up and expect it to work out. You need to actually put in what they recommend as the u value in the figure caption of figure 5a in order for it to work, okay? And you know that you've done it right if you've been incorporating these values like k and IPTG and n. So hint, hint, equation at the dy dt of 2 is not going to be the same thing as equation 1b in the paper. Okay, so once you put that in, everything else should be pretty straightforward. So let's go back to the actual ODE solver. Okay, so everything up to here should be fine. And then here, this is something that you need to put in. So if you remember from homework 3, we ended up solving the equation, but then we wanted the steady state values. And so we ended up picking the last value in column 1, for example, because we know that by that time it's going to be steady state. So this is the same, similar idea here, is we want u to be y. So y, if you're wanting a specific value, you want y of blank comma blank. So the first blank is going to be t, and the second blank is going to be which value in the y array is u and which one is v. So you know which one is u and which one is v if you scroll down to where you define the equation. We say that u is y of 1 and then v is y of 2. So technically, you already have part of this. So u of k is y of blank comma 1, and then v of k is y of blank comma 2 because it's been defined down there with the equations. But which time do you actually want to reference so that you get the steady state values? Refer back to homework 3, and you should be able to get this. Basically, we want the longest time. So that's your hint. Okay, and so next step, like we did in homework 3, we want to normalize, and you have to normalize because if you look at the figure, it goes from 0 to 1 and it's normalized GFE expression. So if you have a non-normalized GFE expression, it will not look this pretty. So you have to normalize. And to normalize this one is actually pretty simple. So you actually have been given the first step. You define max of u, because in this case, max of u is going to be the last value of u. Or yeah, you can just call it straight. It doesn't have to be like a super complicated array. So if you define m1 equals max of u, then u normalized would just be u divided by m1, for example. And then you do the same thing with v. So then you'd have normalized u and v values. And then you can plot that into the semilog x plot. And you should be able to get one of these curves if you do it right. So depending on how you put it in, you won't be getting the blue curve, but you should be able to get either this curve or this curve, one of the red curves, depending on your initial conditions. Okay, so the second part is basically repeating exactly what you did up here. So most of this stuff is the same, but the main thing that you need to note is you need to change this initial conditions. So remember how when we were talking about the graph, we said that these two red curves are both the toggle switch plasmids, so they're both governed by the same set of equations. But the solid red curve is starting from the high state, and so basically if you start from the high state and you like increase the stimulus concentration, it's going to be like, well, I'm already at the top, I can't go anywhere. And then the discontinuous red curved dots are like starting at the low state, and then you give it enough stimulus and it's like, whoop, I'm jumping into the high state. Okay, so same idea here. You can use the exact same set of code that you had from up here down here in order to get the second one of those curves, but you're going to need to play around a little bit with your initial conditions. So you need to have it start at the high state instead of starting at the low state. So for example, if for the initial conditions here you put 0, 0, then you're going to get that one graph. You're going to get this line, the dotted line, that starts from the low state and goes to the high state. So then the only thing that you need to change for the second part is to change the starting initial conditions so that you start at the high state, and then you should be able to get this solid red curve. Okay, so play around with that a little bit, it shouldn't be too bad. And then the final thing that you need to do is to get that blue curve. So the blue curve, remember, is the control plasmid that they mentioned in the paper. So it's not going to be the toggle plasmid, so we're going to use a separate set of equations. And for this, the equations are actually already given to you. So if you look at the equations control, scroll down, not much you have to change down here, I don't think. but everything should be given to you already, and you just need to run the ODE solver. So again, he didn't put this in for you, but you do need an initial condition for this. Oh wait, actually you don't, because the initial condition is already given in here for you, which is 0. But I think this part should run by itself, and you do need to normalize to the max value for each part, for each of these 2 parts, and then graph it. And you want all 3 plots on the same graph, so then remember your hold on and hold off. And then always title, legend, X and Y axes labels. So that should not be too bad, but just think about what I said and try to figure it out. Okay, so then remember your modification perturbation, as always. Modify it in a way that is meaningful. Don't just change some value from 2 to 3 just because. And then so that you can actually describe it and say what you did. But don't overdo it so that the whole system crashes, and you should be fine. So with that, I think we have gone through the code. So if you have questions, please start early. Please come to office hours and ask. Don't wait until the last minute. And good luck, and we hope that this helps.